Hi everyone, my name is Viali Kazadi Mutombo. In this video, I'm going to present about smart transportation platform for private transportation. And this presentation is divided into 5 big parts, such as introduction, related work, smart transportation platform, which is the proposed solution, then evaluation and results, and finally the conclusion. Starting with the introduction, I would like to briefly introduce this transportation domain. As we all know, the transportation domain is a very huge domain, which is divided into 2 subdomains, such as public transportation and private transportation. Public transportation includes a bus, train, subway, boats, airplanes, and so on. While the private transportation includes private vehicles. Talking about private vehicles, here I mention the personal vehicles or the enterprise vehicles. We can also include taxi in private transportation. And the difference between the two subdomains is that in public transportation, there is defined routes for each trip, as the drivers has to drop and pick up passengers at each station, and there is also no need of parking slots. However, in private transportation, the driver decides which route to travel, and there is also need for parking slots when he reaches the destination. As most vehicles in cities are private vehicles, so that means solving the private transportation problems will have a huge impact on improving the transportation system. This is the main reason why we focus on the private transportation system in this research. So the main problems in private transportation are routing problems and parking problem. Because of the lack of optimal routing algorithm and lack of parking slots in some popular areas during some peak time, there are some problems such as traffic congestion, time waste, fuel consumption, and dioxides of carbon emission. So in order to solve these problems, so many researches were conducted. Here I can mention smart parking system proposed by Yadavali, which is an IoT-based parking application to detect available slots. And here the drivers using their mobile, they can check available slots in real time, and the application can also give a statistics of parking slots occupancy, and this is very good. However, the reservation feature was not considered. This is a bit difficult for drivers, because if the reservation feature is not incorporated, this does not ensure the driver that the slots will still be available when he reaches the destination. So another drawback that we found is that the design proposed by Yadavali showed a low quality in terms of effectiveness, extendability, and functionality. There is also another research about IoT-based smart parking system conducted by Kana and Anand. And this is an IoT-based cloud-integrated smart parking system with a mobile app that allows drivers to check available parking slots and make a reservation. So the difference between with our research, with this research presented here, is that the authors focused more on the hardware infrastructure, while in this research we focus more on the software design. Another research was carried out by Balta and Oslake on traffic signaling optimization for intelligent and green transportation in smart city. This is a non-colony based algorithm to alleviate traffic congestion. And the solution reduced delay time, fuel consumption, noise, and the carbon dioxide emission. And this is very good. However, the difference with our research is that the authors focused more on the traffic signalization, which is another aspect of the problem. And comes Dijkstra algorithm, which is a well-known algorithm and which relies on the shortest path principles using Euclidean distance. And this is a very good solution with, when the traffic condition is good. However, when the traffic condition is bad, the shortest path is not always the best because so many people are intending to use the shortest path, and so this path might be congested. So there is another research also which is talking about a randomized path routing algorithm for decentralized route allocation transportation network. This is another research based on random route for each vehicle. And the good thing with this is that multiple vehicles sharing same source and destination will get different route. So this is good. However, a drawback with this is that due to the randomness of the route, some routes can take more time and there can be more fuel consumption than others, especially when the traffic condition is good. So this can have some drawbacks due to the randomness of the route. So that's why in this research we also proposed a smart transportation platform, which is divided into two frameworks. First is a smart parking framework, and then the second part is the congestion-based optimal routing framework. For smart parking framework, we use the clean architecture methodology for designing. And then in order to evaluate the framework, we use the quality model for object-oriented design methodology. However, for congestion-based optimal routing framework, we use the greedy approach. So starting with the smart parking framework, actually let's try first give the specification, the application specifications. Here we say like the driver can initiate the trip and the application recommends him the optimal routes. So the application can also look for the nearest parking lots to the destination, and the parking lot with available slots will be recommended to the driver. And each parking system, we assume that each parking system is based on IoT module. So the driver can reserve and pay for the parking slots before, or also he can cancel or extend his reservation. It can also save some parking in his wish list for later reservation. So based on this specification, we made this use case diagram. As you can see here, we have the driver, we have the server, the camera, the sensors, and the attractors, and we can see the use case here. The driver can reserve, the driver can create his profile and register his car, and so on. And this is the class diagram that we designed based on the use case diagram. And you can see here, actually it's not originally it's one diagram due to the space in the paper, so we decided to divide it into two. As you can see here, the reservation here can have a relationship with parking slots, because a reservation is made on parking slots. And the second part, on the other hand, is the congestion-based optimal routing framework. This is, based on the shortest or fastest path and congestion status. This is to say, if the congestion status is good, the route allocated is the shortest route, or can be similar to the shortest route. Otherwise, the route allocated is the fastest route based on the speed, so and the time to reach the destination. So due to this, we computed the congestion factor of roads within the path, and the congestion factor is can be computed using this formula, such as congestion status and ratio. Here the ratio is the share of the road within the path, and the congestion status also relies on the traffic conditions. So the congestion status can be good, or if the traffic condition is good, the congestion status approaches 1. Otherwise it can be below 0.5 based on the speed. So we can compute the congestion factor of the path using this formula, which is the summation of congestion factor of each road within that path. We made the summation here because the congestion status here, so the ratio here for each path is the share of each road, is the share, as mentioned earlier. We said the ratio here will be the share of each road within the path. So based on this, we can compute the estimated travel time, which is the distance over the speed multiplied by the congestion factor. And the total estimated time can be this one. The total estimated time can be the summation of the estimated time of each road within the path, just in case, just if we compute the estimated time per road, but you can also compute it for each path. And here the optimal routes would be the path with the minimal travel time. So this can also be done using dynamic programming. However, we have to make sure that the congestion factor of each road is always includes the ratio of the roads within the path where it's included. So in order to evaluate, this is the fourth part of our presentation, evaluations and results. In order to evaluate the smart transportation parking, as mentioned earlier, we used the quality model for object-oriented design, which has this quality metrics. So we computed the quality metrics in order to evaluate the quality of the design proposed. And in order to compute these quality metrics, we have to compute first the design metrics or design properties, such as encapsulation, design size, hierarchy, coupling, cohesion, inheritance, polymorphism, abstraction, composition, message, and complexity. So using the design metrics, we computed these quality metrics such as reusability, flexibility, extendability, understandability, functionality, and effectiveness. And this gives us these results. So these are the results of design metrics, and we can see here, based on these design metrics, we got these quality metrics. And as you can see here, we got for the proposal framework, apart from the understandability, which gives us a very low value compared to the smart parking system proposed in 1, because our results was compared with the results with the smart parking system proposed in 1. You can see here that the values of understandability is low because of the complexity of the proposed framework. However, other quality metrics shows a big improvement. And you can see here the proposed framework, the total quality index of the proposed framework is much higher than the one proposed in smart parking system by Yadavali. So in order to evaluate the optimal routing framework, we carried out the simulation using Sumo and MATLAB, and we used the TRACEI for MATLAB in order to interconnect Sumo and MATLAB using a TCP/IP based connection, which is a client-server connection. And using the TRACEI for MATLAB, we could interact with the Sumo simulation using MATLAB. We could interact in real time. And we computed these metrics such as travel time, the fuel consumption, and carbon dioxide emission. And we compared two different algorithms, such as that Kestra's and our framework proposed here in this research. As a matter of fact, you can see here that from the beginning, the simulation results give us different results. However, here with less vehicles, with less transportation load, the results are almost similar because the traffic condition is good. So we got similar results for both algorithms, but with high traffic loads, we can see a big improvement here with our algorithm. So our algorithm shows a very big improvement. So you can see the travel time, and same with fuel consumption and the carbon dioxide emission. So you can see a huge improvement in terms of carbon dioxide emission. So in conclusion, the main objective of this work was to propose a smart transportation framework, which was divided into two frameworks, and then we used this methodology, and as you can see, the results shows an improvement for both parts. So this is the end of this video. Thank you so much for your attention, and all your questions will be welcome. Thank you.